Today we have Srikanth Tamil Selvan from IBM, who's going to do the session today. So join us in welcoming Srikanth. So he, like throughout his career, he has taken up challenges that aims to improve productivity of developers. He has extensive experience in leading high-value research projects and teams throughout all the phases of definition, planning, implementation, and delivery. He has led multiple projects with global teams to successfully develop and deliver value through constantly new solutions, platforms, algorithms, and models for infrastructure, maintenance, compliance, AI testing, and application modernization. For his contribution, he had been awarded multiple outstanding technical achievement awards and research division awards. He is also recognized as an IBM Master Inventor for his contributions to IBM focused patent portfolio and mentorship. So far, he has submitted 60 plus patents at the USPTO office and has published around 20 referred papers. We are so happy to have you today, Srikanth. It's a pleasure having you today and getting to listen to you. Over to you. The floor is all yours.
Sure. Thank you guys for the kind introduction. So I'm also equally happy to be spending time this evening with you guys to share my experience and understanding of on large language models. So I hope many of you guys must have tried ChatGPT in the last few weeks and months. You guys must have been awed by its performance. And I hope many of you guys are aware, or like maybe this might be insightful for you, that these are actually powered by large language models. These tools are powered by these large language models. So we'll see how they perform. So that I'll cover that in the initial part of my presentation. And then we'll also try to get a brief understanding of how these large language models came into existence, like what were the predecessors. So we'll just look into certain types and what are the common techniques applied. And at the end, what I will also do is I'll just give you a brief introduction to one of the metric that is used to evaluate these large language models on its own, and then some references of how you can get started. Okay, so that's what I plan to do. Okay, so large language model is actually a task of predicting what comes next. So as a simple example, so if you see a sentence with the following words, haven't seen in a while and I, okay, so when I stop at that, I think that there can be multiple words that can fill the next word, right? It could be like I hope, I wish, I thought, I am. Okay, so there are multiple possibilities. So the task of language modeling is actually to predict, given some sequence of words, let's suppose like x1, x2, and right till x. So where 1, 2, etc. are the time steps. So given words until a time step t, you want to compute the probability distribution of the next word. So that's the whole funda behind this language model. And this task, and there are like multiple ways to do that. So that's what we'll focus on more in detail in the coming slides. Okay, and then you also need to have a notion of vocabulary. So vocabulary is nothing but just all possible words. So okay, so the probability of the next word that comes from some defined set is what this whole task is about. So why do we need a language model? Because you want to identify a good grammatically correct sentence versus not so great grammatical sentences, so that when these AI tools try to interact with you, they make sense. So for example, it can be a conversation system where you are trying to have a conversation, and then it should give you, it should not only fetch you the right information, but it should also be coherent, and it should make sense when you read it. It should not make you even more troubling. Otherwise, you can always look into some IR system, basically information retrieval system like Google search, where you can just look for some facts. That should be fine. But then when you want to have a question answering system, a conversation system, or a translation system, you need a grammatically and semantically correct sentences. So that's why these language models are important. So then they can give high probability to grammatically semantic relevant sentences, and low probability to the other ones. As an example, so the sun rises in the east should always be given more weightage, the probability of it coming compared to the sun rises in the west. So unless you want to fool or you have a scenario where you want to come up with all wrong answers, the probability of the former is always greater than the later. Similarly, the sun rises in the east, the probability of this set of words coming together in this particular sequence should always be more than sun RISE in the east. So these are some of the reasons why you need a language model, so that you can build a good generation system. At a high level, so there are like two types of language models. One is statistical based, and in term like this n-gram based one is a very popular one, where n-gram can be replaced with 1, 2, or any number. So basically what it says is like this n-gram based model, what it tries to do it is like the probability of the word to be predicted should be dependent on what number of previous words or tokens. So the n refers to that. If you want the current word to be predicted based only on the previous word, then n is equal to 1. If you want the context window, so where by context I mean what is the previous set of words that you want to look into, that's what I'm calling as context. If you want to consider 3, then it becomes 3. So this is how it started, and then very recently, after all this great innovations with a back propagation algorithm, etc., neural network based models started to become very popular. Okay, and there what we were able to achieve was, you don't have to explicitly try to come up with this the statistical patterns. You just feed the data and then have a very generic objective functions that can teach the neural model of how to learn these sequences, okay, so that it can fill in the future by itself correctly. So this became very popular, and that's what is powering most of the AI systems currently, especially the generation systems. Before we go into the neural model, let's spend a couple of minutes on this n-gram language model, so that we can get a fair idea of how that can be done in a very intuitive way. So the n-gram model, like I said, it works on the assumption that the probability of the word to be predicted depends only on the previous n-1, where n is something that the user configures. And the basic way it works is, if you remember from our high school maths, it works on this simple chain rule of probability. So what it says is like, to find the probability distribution of words x1 to xn, all you need to do is you first find the probability of word x1, basically your first word, followed by the product of the subsequent words given the previous words. So as an example, you can see from here. So if you want to find out the probability distribution of I went to the ground. So if your probability is high, then it means like it's a good valid sentence. If your probability is less, it is not so good. What is the threshold is something that you will learn over time. Like if you have enough corpus, when I say corpus, it means data. It can be books, Wikipedia, anything. You train on that and you will figure out what is the accepted threshold. Okay. So if you have this, then if you apply the chain rule of probability, it will be something like taking the first word. So basically a probability of I being a starting word multiplied by probability of word went conditioned on the previous word being I. The probability of then multiplied with probability of the word to given the previous words I and went, multiplied by probability of the given the previous words I went to, etc., until you try to fill in the necessary words for which you want to calculate the probability. Okay, so this is how it works. And then how to calculate the probability? So one simple way is used to look into the frequency counts. Here as an example, you can also try this. You can go into this Google Boost Ngram viewer. What it will give you is for the different years, for the for the different years, you can find out the frequency count of a particular word that you are interested in, compared to all the different words that appeared in those years. So as an example, if I am interested in, right, I went to the, so you can see like this kind of words, I went to the frequency of them occurring in the books of 2000, 2002, etc. This is the kind of information you can see. And you can see some of the sentences that were formed with this prefix. Okay, so you can use this kind of information to just validate the correctness or the acceptance of this particular sentence. So for example, given the initial set of keywords, I went to the, and you want to understand the probability of right market that can appear after the initial set of words I went to the, you can just simply look into the counts of right in this ngram viewer by looking into what's the probability of I went to the market that appeared in the corpus given all the words that had right I went to the. Okay, but then there can be many things that can come after I went to the, right? Market is just one option. So this gives you an idea, right? So this gives you some value that gives an indicator. Okay, so is it possible that market can come after I went to the? So this was the approach that worked right in the early literature of language modeling. And then people started to write experiment with different context windows. So instead of 2, can we have 3? Okay, then people felt like for long sentences, especially when you have like a very formal document, some of the words have a context much earlier in the sentences. So then they started to keep the context window larger, like 10 words, 15 words, etc. But then people always found they were right. There were always a drawbacks. People were improving, but then there was always drawbacks. Okay, so that was how the literature was, and then people used to hate this kind of thing. For example, there can be a good relevant sentence, but you might not find them at this point of time in your corpus. But that doesn't mean it's not a valid corpus. For example, this, if you try to type this particular keyword, keywords or this phrase in the Google search, can I use diffusion models to train a neural machine translation system? Your corpus did not have it, but that does not mean it's a invalid one, right? So that was like one of the big drawback with this n-gram language models, because the amount of patterns that you could learn and the computation power was right, it's less to the real world need. So this brings us to some of the drawbacks with this kind of models. So one, like I mentioned, so you definitely need a large amount of data. So at that time, people digitized a lot of books and then news articles, etc. So it was helping, but then these kind of models are resource hungry, basically data hungry. So you need to have like possibly all kind of things to have some good right accuracy. And then the computation complexity kept on increasing. So as you start increasing the context window, you see, right, it's a product of right so many word conditions. So the computation cost and the storage cost is too heavy. So that's another big drawback with this n-gram model. And the third thing, like I showed in the previous slide, right, like it might not work out if it hasn't seen some word, right, that without that context, so it will fail. And also certain times some of the words they play a different role in different context. So these kind of models are very bad at right disambiguating such context that can have words that can have different meaning in different context. So yeah, so this led to right people exploring other ways where they did not want to right really come up with features, look into defining many of the patterns, etc. And around that time, this neural networks also started picking up. So there were good improvements, and it was feasible to run them in simple CPUs, and now these days in GPUs. So this task was then right tried using neural networks. So this led to neural language model. So yeah, so like I said, the intention is not to try to find patterns or features by yourself, but try to let the neural networks learn those complicated patterns and then understand like how to find the sequence, form the sequence, and then maybe use that to evaluate if the right what word should come after a sequence of words. Okay, so the basic way that it works is you try to learn a representation of words and then sequence of words. So this led to this effort on right how do you best contextualize right how do you best represent the information of each words to these vectors, and they're generally called word embeddings. And in future, there are also work that try to come up with sentence embeddings, because for many of the similarity kind of tasks, sentence embeddings was better. So instead of trying to learn individual word and then their representation, they try to find out like for frequently occurring sentences like their representations. So it will become easier for many of the tasks like similarity matching. And then, like I said, the way it will work is you will have a neural network, and then you will take your sentences, pass it on, token by token. Token and word can be right interchangeably used, but there is a subtle difference. Sometimes you might split the word into smaller tokens. But for this discussion, we can consider that each word will be given as input to the model. And what it tries to do is it tries to and then learn the sequence by itself without you specifying anything. Just the model, it will learn where you will penalize, for example, try to give a sentence and try to introduce some task, like trying to predict some words in the middle or at the end. And then if it fails, then you will penalize it. So the information is back propagated throughout the network. And then right, the model slowly will start to improve. Okay, so that's how it started, this whole neural language models. So initially, some of the networks that were used was RNN and LSTM, but these days, if you look into the literature, it will be mostly transformers. Okay, so even all the recent AI tools that you're seeing, be it GPT-4, ChatGPT, Bard, Llama from Meta, anything, all of them are powered by this architecture called transformers. Okay, so this is a very simple view of this transformer, but this was a game changer. All the great innovation that has happened in text is actually because of this single architecture. If you guys are really interested, you can look into the blogs around transformers, how it works. If you can just learn how to write create this kind of network, how they work, right? I think you will get a very good grasp of language model and how it works. Okay, so there are like 2-3 innovations that came here. So one of the key ones with transformers was, so until then, people were primarily using something called RNN and LSTM based neural network architecture. So basically, you have to rely on the word is always relied on the previous set of words. Okay, but then with this one, what they said was, given a sentence, I will treat each word separately. Individually, I'll try to learn the importance of this word in the context of other words that it coming with. So this concept is called as self-attention. So it helped folks to paralyze the learning task of each token, and then forward have multiple layers on top, so that the representation was more dense. Okay, so that was one big innovation that came. And like I said, like it lose the timestamp compared to earlier one to gain that parallelization power. But then they also introduced something called as positional embedding. So basically, for each of the word, there will be a vector that will represent the semantic information. But they also append something additional vector that will tell you the position. So for example, like it can be some function that is incremental, so that the first increment can be put for the first word, second one to the second word, etc. So that's called as positional embedding. So combining the positional embedding to each of the word embedding, that gave a flexibility to retain the sequence when you want to generate. And then there was this whole thing about cross attention. So for example, once you give us input, for example, in this case, write a function to print hello, you will learn some representation. But then to, let's say, translate them or write a code about it. So basically, any generation task that you have, you will need to start having a way to map for the generation task. How do you map the learn to representation? So there was this concept called as cross attention. So basically mapping the representation of the encoder, which is trying to come up with the embedding representation for the input, as an input to the decoder, which tries to use that to translate into something else. In this case, it is writing a code for this natural language prompt, but it can also be a translation to Tamil or other languages also. Okay. But to map, there was this concept called as cross attention that was introduced. And then this whole other small things like this kind of architecture, even though people have seen in silos, showing them this kind of thing actually helps in better semantic capturing, right, was the biggest innovation. So this really changed the landscape. Immediately after that, people just applied transformer on all tasks. Like basically this was introduced in the context of translation, but then they were able to say that they were able to see improvements on any language based task. So that powerful it was. Okay. So this actually led to the what we now are seeing as a large language model, or sometimes you might be keeping on hearing a concept called as foundational model. The term was coined by Stanford team. So the reason behind this is in the traditional way, before transformers, most of the people used to take this particular approach. Like, so for example, if you take a simple classification task of given some movie reviews, you want to say whether it is positive review or a negative review or whatever, right, categories you want to have. So people will generally try to fetch a lot of data and then try to annotate like this data or this content means positive, this content means negative, this content means neutral. All right, somebody will create this kind of information. A lot of effort went into creating a big corpus of this annotated data that you would feed to a neural network to get a good classification system. But then many of the things about the final classification is based on understanding those sentences, right? So that, for that, this kind of large language models helped a lot. So what they said is, don't spend a lot of time on coming up with annotation data, because you will have to hire few people, teach them how to annotate, right? Make sure they don't make mistake. There is so much overhead. So maybe you can just find some good annotators and then give them very less data set, but then make the model have a good understanding of the sentences, so that with few annotation, it will learn, oh, okay, so if this is my sentence, then if I'm told like this, I should be able to classify so and so. So try to lessen the overhead of having a huge annotation task and availability of such good rich data. So what people did is took all the digitized data, basically all the public internet data like news articles, Wikipedia, etc., and then started to introduce some simple tasks. For example, I will teach the model, given this set of words, I will mask certain words and then try to ask the model, predict them. So basically, you don't need external people to have this kind of task, right? Basically, you have a sentence. So this sentence can be simple like recent paradigm in NLP transfer learning. This is something that you already have, right? Let's suppose this comes from my book. You don't need somebody to have any annotation. All you need to do is just drop certain words from here. In this case, let's suppose I'll give the sentence as now next paradigm in blank hyphen transfer learning. And then I'll try to see if the model can predict NLP. Obviously, for the very first time, it will not. But then later on, right, I will say that, okay, it is supposed to be NLP, but I'll try to ask the model to predict some word from the vocabulary. So in this case, recent paradigm in science also could have been the first attempt, but then you teach the model, no, in this context, it should be NLP. So then you penalize. So this is called self-supervision. So the reason why they coined the current models as like foundational models, the large language model, is because of this auto-regressive way of learning stuff without any external supervision. So once you have the model that can learn how sentences are formed, then you just work with a few resources to come up with that fine-tuning data. So this is called as fine-tuning. Basically, the model itself has good power in coming up with a good sentence formation. So in a way, that means like model knows how to form what makes a good sentence. So it itself is a good pre-trained model. Then you just add this additional label data to just fine tune that model with some additional layers. So earlier your task would have been trying to predict this kind of word, but now you wanted to classify between like positive, negative, or neutral. So you'll add a few additional layers. So generally you'll hear something like feed forward neural, feed forward layer followed by a softmax layer. Okay, so if you just look into the literature, you'll hear this term. So that will help you to treat this as a classification task, but with very less annotation data for fine tuning. Then you get a state-of-the-art classifier. Okay, so this process of like learning by itself without any external input led to this term called as foundational model, which is very much used now. Okay, so I was able to motivate. And how big are large language models? I said like these are like large language models, but how big are they? So you can see this chart. It's increasing rapidly, right? Just few years ago, there was like people are playing with simple like 15 million, 30, 90 million models. But now if you see like the publicly known one is from Google, Palm, which is like 540 billion models. So this 540 billion parameters, to understand parameters, just take a course on neural network. So you'll see that there is a concept called weights and bias associated with each neurons. So that's what makes us parameters. The larger the parameters, the more information that it can store. And we have seen that consistently they perform better easily on many of the tasks. Okay. There's also the GPT-4 and chat GPT, which is like giving state-of-the-art performance in many generation tasks, but they haven't revealed any details about them. But many people are thinking that might also be 1 trillion parameter model, but we don't know. Okay. So this is the general recipe of like many of the large language model currently. You need to decide the architecture. So like transformer had two components, right? There was encoder and decoder. All the GPT models currently that you see from OpenAI, Microsoft, etc., they are only using the decoder. So they are saying like, I don't need to come up with learn a representation of my sentences to generate something. I will straight away start with the generation task itself. So I'll only look into the decoder part. Okay. But many of the other models, like from Google, there is this FLAN model, which is an encoder-decoder approach. Also from Amazon, there's an encoder-decoder approach. So there's a big debate on what works well. But if you see the performance-wise, decoder-only model from OpenAI seems to be doing really well on almost all the generation tasks. Okay, and then there are like I said, for the self-supervision, there can be multiple ones. So you can have words dropped randomly in a sentence, or you can like make sure the model sees only the words so far and doesn't see any words in the future and try to predict. So this is called as casual language modeling. So that can be another way. But there is also other training objectives, like given a sentence, can you predict the next sentence? So people are playing with this kind of training objectives to come up with a good pre-trained model, which can be fine-tuned. And obviously, data is a critical one for coming up with a good language model. So if you just look into the literature, you will just see that so many petabytes of information are being crawled and made available for this learning. Okay, and obviously, compute is a big factor, which is why very few players are able to do well. So if you see, there is Microsoft, Google, Amazon, to an extent, IBM, but there are not many players. Very few startups like U.com, Niva, few of them are in the play, but not everybody have access to this kind of compute. So you need like really large GPUs, like NVIDIA is like, right, is like the market leader there, providing GPUs and right, almost everything, almost like just the big companies have this kind of facility to train really large model that can address many real world right, scenarios. So what's the point of doing all this one? So obviously you guys must have seen GPT-4, so this might not surprise you, but I'll just tell you some of the things that happened in the past. So what people used to do is like they'll have some good model and then they'll start giving very limited samples. For example, if this is a translation task, they'll give a English, for example, English to French. They'll give a English word sentence and then try to find a French sentence. They'll see, okay, if it is not right, then they will just update the model. Okay, so this was the traditional way of doing it. What has happened now is just take the model which is really doing well, just give the task as a description and just prompt. Okay, it has seen enough information about translation and other things from the publicly given articles. You don't even have to give an example. You don't even have to fine tune the model. Just say translate English to French and then say cheese. It will know what's the French equivalent of it. So this is called as zero shot setting, where you are not even giving one example to the model of how to perform a task. All you are saying is, this is my task name, translate English to French, and here is my keyword for you or a sentence for you to translate, and it does. This is such a big leap. There are a lot of studies that are happening now to understand why this zero shot setting works, why this in context setting works. There are no great answers yet, but this itself is a good research study now that is happening. And for certain cases where the task is not that popular, what you can do is like specify the task, give certain examples, like translate English to French, give 3 samples, and then give the given word or a sentence. It will come up with the translation. So this is called as few shot learners, where you are giving few short examples and the task description as prompts, and this large language model should be able to get your thing done. Okay. So yeah, this is a study. This is a good paper from OpenAI. If you open it, it will you'll be able to. The title of the paper is "Language Models of Few Short Learners." If you're interested in studying, you can go over, and it has given a lot of experiment insights on how these large language models are able to perform really well, very quickly with on zero shot, one shot, and few shot. As the model sizes increases, their performance is like way high, as you can see here. 175 billion parameter model compared to 1.3, their performance against zero shot or one shot or few shot is like exponential. Okay, so we saw a lot about large language models. So let's see what people use to evaluate these large language models. A quick disclaimer, there's no great way to do it, but this is what people use it in practice. So there's something called as perplexity. So it is just, you can think of it in a very layman terms. All it means is how surprised the model is when it sees a sentence that it has not seen before, how perplexed they are. That's all it is. And it can be calculated by this simple formula. So basically you try to identify the average log likelihood of those sentences normalized by the total number of unique words in your test set. Okay, that's all the formula is. We can take a simple example. So for example, if you say like you trained a large language model, and then let's say these 4 sentences are your test sentence, and you want to understand how perplexed the model is, you can just try to find out the probability of each of the word to be predicted by the model, take a log of it, and then you can do average log likelihood of them, and then normalize by the total number of words, in this case which is 23. You will get some number. So the lower the number is, the better the model is. That means right, they are a good generalized large language model. So so what number is good and etc. So people have been following the literature, so they know the performance of some of the popular models, and then they test against them. So if you have a well-defined test set and then you compare with the previous versions of large language models, and if you're doing better, then you can be sure that your model is good generalized. But then this, like I said, this is not the only right way to evaluate a model. You are coming with this model actually to perform a downstream task, for example, translation, conversation system, right, story writing, etc. So then actually you try to fine tune this large language model for a task and try to evaluate. That's what practically people do. But then to even know when to stop the training and whether you are at a place, this is kind of a soft metric. So this is like a one good metric that you have currently. Okay, in case you guys are excited about this, and if you want to know like where to get started with accessing some large language model in the public community, Hugging Face is one good option. You will see a lot of models being contributed from IBM, Microsoft, Google, Amazon, etc. here for different tasks. So look into this page called huggingface.co/models. Basically, Hugging Face is a company, but they are really into democratizing AI. So they try to replicate many of the state-of-the-art papers and make the model available for everybody. And many of the researchers also, they want to help the community. But then, yeah, like company also has to decide which models they put online. So you won't find GPT-4, GPT-3, etc., because that needs to be productized and they want to make money out of it. But you'll find many of the other people, they just are interested in democratizing. They'll put the state-of-the-art models in here. So this became like somehow community adopted place for hosting models and right weights. Okay, so I hope I was able to motivate you why language models are necessary and right how they are powering current AI systems. And like I said, there are like not many great ways of evaluating them, but perplexity is one. But to really be sure whether you want to use a particular language model, always fine tune for a particular task and then do it. And to get started in this area, I would advise you can look into a course from Stanford. They have a course dedicated on language model. And then you can also look into Hugging Face. They themselves have good blogs and then good APIs and interface to try out few things. Okay. Yeah, that's all I had for this session. Okay. So if you have any quick questions, you can ask me.